started. Right? So last class, if you remember, we talked about two of them. We talked about the step function, or what we call the unit step function, and we define the unit step function in this form. I mean, usually in EE207, a lot of things are easier to describe graphically rather than mathematically. I mean, if you look at this from first sight, you'll have to look carefully and figure out what it means. But in a graphical way, it's quite simple. It looks like this. Okay, where this is equal to 1, this is equal to 0, and that's basically u of t. Right? Now this is u of t. The general form of the step function is a shifted version. So if I ask you what is u of t minus t0, it's exactly the same shape. Changing colors here. Let me use black for the axis and red for the curve. And this is basically how u of t minus t0 look like, okay, where this is equal to t0. This is basically the definition of the unit step. And then after that, we talked about the direct function. We said the direct function is not really a function by itself. It is, in fact, obtained by, this is how you can define it, by the way, if you wanted to define it mathematically, or you can represent it in terms of the unit step function. And this is, I remember the last thing that I think we talked about last class. We said that direct function is nothing. I didn't write this in here, I think. Yeah, I didn't write it, okay? But I'll add it. In fact, direct function, and the reason why it's called direct is that it's the abbreviation of rectangular. So direct function, rect of t minus t0 divided by capital T is defined as u of t minus t0. Sorry, u of t, hold on, let me see, u of t minus t0 divided by capital T plus in here minus u of t minus t0 divided by capital T, okay? Yeah, this is basically the definition of the direct function in terms of the step function. In fact, I remember last class I erased it, but we only talked about the situation in which, this is how direct function looks like, right? Where this is t over 2 and this is t over 2. But the general form, this is rect of t over capital T. Okay? The general form is that you have a shifted version of this. So you subtract there t, or you put t minus t0, where you'll end up with this, which is defined in terms of the step functions in this form. Okay. Now, are those the only two singularity functions that we're going to study? No, there is a third one, which I think is as important as the step function, yet it's more difficult to understand. And the reason why it's more difficult to understand, or let's say work with, is it's because it's more theoretical rather than practical. I mean, this step function, you can go to the lab and you can generate it. The problem with the next function that we're going to talk about is that it's purely theoretical. You cannot create it in the lab. You can simulate it. You can create something that appears to be, trying to resemble this function, but you cannot simulate it perfectly in the lab. Okay? What is that function? It's called the unit. Sorry, I don't know. For some reason, I have them flipped. I will talk about this later. Okay. The next function that we're going to talk about is called the unit impulse function. Unit impulse function. Now, from its name, it's unit. It has some characteristic of it has the value of 1, and you'll understand what is that. Where does the unit appear in that impulse function in a few minutes. Okay. But anyway, it's called the impulse function or unit impulse function. I can define the unit impulse function in two ways, either graphically or mathematically. If I start with the mathematical form, you're probably not going to understand it and you're going to struggle with it. So let me look at it in the graphical form, and then we'll see that the mathematical form makes sense once you understand the graphical form. What does the unit impulse function look like? Think of a rectangle, just like the rect that we talked about, but a thick, thin rectangle like this, right? Where you define this rectangular function, this rect, in a way such that it is 0. Let me, in fact, erase let me erase the whole thing and put the axis in black. The axis in black and sketch this rectangle in red. Let's think of a rectangle that is centered around 0 and around the y-axis, but this rectangle is formed in a kind of a special case or a special way, where it starts, the rectangle function is 0 from -infinity all the way to this point that I've marked in here. And at this point, what happens is it goes to a specific value in here and remains for that remains at that value for a specific period and then goes back to 0. Now I will assume that this point in here, okay, has the value of epsilon over 2. And usually whenever someone tells you I'm going to give you a value that is equal to epsilon, what does epsilon represent in math usually? Yeah, so I cannot see the names. Abdurrahman, what does epsilon usually mean?
It's the definition of a limit.
Yeah, which means it's a small value.
Yes.
In fact, we'll set the epsilon there to go to 0, right? But you're absolutely right. Usually, epsilon is used in situations where you want to indicate things that are small. And this is why I'm using epsilon there. So let's say that this rect function increases at the value of epsilon over 2, where epsilon is a value. It could be 1, it could be 0.5, it could be 0.2, it could be 10. Anyway, it's a real value. And then this rect function, as I mentioned, or this rectangular function, goes to a value, a specific value, a value that I'm going to talk about in a minute, okay? And continues for that value or at that value for a while, and then goes down at epsilon over 2. So in fact, the width of this rectangular function is equal to epsilon. I start at minus epsilon over 2 and end at epsilon over 2. So the width there clearly is epsilon. And let me define the height of that rectangular function to be equal to 1 over epsilon. Now, without telling you what epsilon is, if someone asks you, what is the area under that graph? Or if I integrate this graph, if I integrate this function here, how much area do I expect under it? Again.
It's simply epsilon times 1 over epsilon, so that's 1.
Exactly, it's equal to 1, regardless of the value of epsilon. So clearly the area in here, area is equal to 1. Okay? Now, the definition of the unit impulse function is exactly this when you set epsilon to go to 0. As you make epsilon smaller and smaller and smaller, what happens? The width here goes to 0. What happens to the height? It will go to infinity. 1 over 0 becomes infinity. So if you reduce, think of it this way, if you reduce epsilon to 1/2 of its width, of its current width, this is what you'll end up. If you reduce it more, it becomes like this. If you reduce it more, I don't know if I'm good in sketching or not, but it becomes like this. The definition of the unit impulse function is exactly like this when the width there becomes equal to 0 and the height is equal to infinity. So the area, you see, if I just defined the unit impulse function to be equal to a rectangle with a width that is equal to 0 and a height that is equal to infinity, and ask you how much is the area under that unit impulse function, you're going to tell me, I don't know. Why? Because the area under that curve, I'll have to multiply 0 by infinity. And 0 by infinity is not equal to 1. It's not equal to 10. It's not equal to infinity. It's not equal to 0. It's undetermined. You cannot just say 0 multiplied by infinity is equal to 1, for example. It could be anything. You cannot just determine it just by looking at the 0 and the infinity. You can only determine it if you look at the physics of the problem. Where did the 0 come from and where did the infinity come from? The 0 came from the fact that I have a width of a rectangle that went to 0. And the height became infinity because I had the height being equal to 1 over epsilon. So regardless of what the height is and what the width is, their product will always be equal to 1. You understood the unit impulse function? This is basically the unit impulse function. It's basically nothing but a function that is always equal to 0 except at one point. What is that point? T equal to 0. Now, how much value does it have at t equal to 0? It has a value that is equal to infinity. But this is not usually how they define it mathematically. They define it mathematically in this form. They say that the unit impulse function is always equal to 0 for all values of t that are not equal to 0. Any value of t that is not equal to 0, that unit impulse function is equal to 0. But I don't stop. If I just lift this, then if x of t is equal to 0, this could be the unit impulse function, because this x of t is equal to 0 is a function that is always equal to 0. Or let me say it this way. Just by saying that the unit impulse function is equal to 0, if t is not equal to 0, I could put any value for the unit impulse function at t equal to 0, where, for example, I could put the value of the unit impulse function to be equal to 0.3 or 1 or 5. But this is different from the unit impulse function that we are defining. The unit impulse function must have a value at t equal to 0 that is equal to infinity, such that if you integrate the unit impulse function from minus infinity to infinity, what are you doing? You're integrating 0 everywhere, except for one point, which happens to be at t equal to 0, which has all of the area of the unit impulse function. Yani all of the area. You see, when you integrate any shape, when you integrate any shape, any function, you are finding how much area is under that function here. It happens that the unit impulse function has all of its area concentrated at one point. What is that point? That point is t equal to 0. So all of the area is concentrated at that point. Only at one point, there is some area, and how much is that area? It's equal to 1. And this is why the unit impulse function is defined always using those two things. You cannot define it using only one. There are an infinite number of functions that will satisfy the second one, but not the first one. For example, this. Minus 1 over 2, 1 over 2, and 1. If you integrate this function from minus infinity to infinity, you'll get this area, which is equal to 1. So this clearly satisfies this. But it doesn't satisfy the upper one, because this is not equal to 0 everywhere except at 0. Okay? And there are also infinite number of signals or functions that will satisfy the upper one, but not the lower one. For example, as I mentioned, if I have a signal that looks like this, I have a signal that looks like this. It's 0 everywhere. Let me just do this. It's 0 before and 0 after, and it's equal to 2 in here. Only at t equal to 0 is equal to 2. Right? This will satisfy this, but it doesn't satisfy the second one. If you integrate this one, by the way, from minus infinity to infinity, how much do you get? Anybody knows? If you integrate this signal, from minus infinity to infinity, it's the area here is 0, the area there is 0. So I'm integrating something like this, the integration from 0 to 0 of 2 dt. How much is this equal to? Yeah.
0.
0, absolutely. Okay. So clearly this is not the impulse function. The impulse function does not have a value at t equal to 0 that is equal to 1 or 2 or 1,000 or a million even. Because no matter what value you put in here that is less than infinity, whenever you integrate that value from 0 to 0, you'll get 0. The only value that you can integrate, which may result in some area that is not 0, is if this point goes all the way to infinity. Okay? So this is the definition, the mathematical definition of the unit impulse function. Okay. Now let's talk about, we'll spend some time. Now I have spent about 16, 17 minutes on this, and we'll probably spend the next 15 minutes even on the unit impulse function, and we'll see some of its properties. And the reason, you see, I mentioned that this is theoretical, because you cannot create in the lab a signal that has, even at a single point, a value that is equal to infinity. If you try to simulate this signal in the lab, probably the best you can do is something that looks like this. And before you reach 0, you'll go to a very high value and then go down immediately after 0. And for example, the width in here might be 1 microsecond, and the height there might be equal to 1,000 volts. Maybe something like this. In fact, it even has to be 1 million volts, something like that. Okay, maybe something like this. This is the best you can simulate the unit impulse function. That it looks like a pulse that happens at t equal to 0 with a very small width of 1 microsecond or 1 nanosecond or so, with a very high voltage. But certainly you cannot simulate a signal in the lab that looks like a rectangle with 0 width and infinite height. No matter what you do, you're not going to be able to simulate it. So let's look at, let's discuss the unit impulse function in more detail. Why do we need it, by the way? Why are we defining it since we cannot create it in the lab? The unit impulse function, gentlemen, has a lot of uses, let's say, especially in signal processing, in courses that use or that work with systems and signals. The unit impulse function is a fundamental signal that you need to understand. You cannot escape it. If you're an electrical engineer, you need to understand and work with the unit impulse function. Okay, it's something that you cannot get away from. Okay. In here, this is the unit impulse function. In here, the difference between the upper and lower one is, as I mentioned, this part is still working on it, so it's not finalized. Okay, this is the unit impulse function at t equal to 0. But in general, we're interested in a unit impulse function that exists at some t0. Yani basically, this is how the unit impulse function will look like. Right? Now, how am I going to sketch it? And typically, for example, if I'm working with the unit impulse function, how am I going to sketch it? I'm not going to sketch it like a rectangle. You'll always see the unit impulse function, gentlemen, sketched like an arrow. If you see something that looks like this, understand that I'm talking about the unit impulse function. One of the things that many of you probably understand, but will still make a little bit of a few mistakes here and there until you understand, or let's say, you master completely, is if I ask you, what is the magnitude of this unit impulse function? It's equal to the area. If I ask you, what is the height of this? What does the arrow here mean? It means that it goes to infinity. Clearly, I'm not going to draw a line that goes to infinity. So the arrow basically means that it has a height that goes to infinity. But the magnitude of the unit impulse function is equal to this value. It's equal to the area under it. Because you could have a unit impulse function that has an area that is equal to 2 under it. If I define this, so what is the definition that I had there? In here, okay? If I thought of this, you see this definition here? If I think of a different function that has the same width of minus epsilon over 2 to epsilon over 2, but the height there is not 1 over epsilon, but 2 over epsilon. What will the area be now in this situation? It will be equal to 2. Now this, how do I write it simply? This becomes equal to beta of t. So the 2 there represents the height, or not the height, I'm sorry, the magnitude or the area under this function. The 2, the number that multiplies the unit impulse function, basically represents how much area is under this function. The unit impulse function always has an area that is equal to 1 under it. If you multiply it by 2, think of it as you're making the height not equal to infinity, but you're making the height as equal to 2 infinity. Now, one of you probably will say 2 infinity is the same as 1 infinity. Yeah. From a logical point of view, yes. But from a mathematical point of view, 2 infinity is higher than 1 infinity. Okay? So anyway, the important thing is that the magnitude or the magnitude of the unit impulse function is always equal to 1. And if you need a unit impulse function that has a magnitude of 2 or so, just multiply it by 2 or multiply it by 3. And if you need a unit impulse function that doesn't happen at t equal to 0, just shift it by t0, t minus t0. But the same 2 definitions that I have there also apply here. Exactly the same definitions. Right. Okay, now let's talk about some of the properties. And I want you to be open-minded here because the properties may not seem to be very clear. And in fact, I don't want you to see the answer because I want to discuss them. The first property says the following. Let me ask you this. If I have f of t, any function f of t, whatever, sine, cosine, whatever, any function, and you multiply it by rict of t divided by capital T, okay, and t divided by 2. Okay. Now we know that the rict function has a width that is equal to 2. This rict function has a width that is equal to 2. If this is equal to sine or cosine, cosine, yeah, cosine. Cosine 2 pi t, for example. And someone asks you to sketch this. How will you sketch it? Can anybody give me a hint how to sketch it? تفضل حسين.
Where the rict is 0, cosine will be 0.
Absolutely right. Yes. And where the rict is not equal to 0?
Cosine will be multiplied by 1.
Exactly. What you said is absolutely right. What Hussein mentioned is this. He said that this is either 1 or 0. Right? It's either 1 or 0. It's 1 in a specific range between -1 to 1. And this basically, if you sketch this is how it looks like. 1 and 1, and it has a height of 1. And the cosine is just a cosine. Let me just sketch it under. Something like that. So, sorry, the sketch is not really good, but I assume that you understand the concept. Okay. Now, clearly, this is equal to 0 here and 0 there. So, whenever you have direct equal to 0, what will it do to the cosine? It will basically, the product becomes equal to 0. And if you plot the product, I know that it will be equal to 0 in here and 0 in there. And inside the region where the rict is not equal to 0, where it's equal to 1, I will have whatever shape of the cosine. And something like this. I don't know if I can sketch properly or not. Maybe something like this. Okay? And then go back to 0. So this is basically the product of the two. Now, because the rict function has a region which is not equal to 0, that is wide, yeah, what it did when you multiplied it by another function is it limited that function to a specific region, and everywhere else it set it to 0. This is in fact one of the uses of the rict function, is that if you multiply it by a function, you make all of that function equal to 0 everywhere except for a specific region where the rict is not equal to 0, where you end up with that function alone because it's multiplied by 1. Okay. Now, the unit impulse function is doing something that is kind of something similar to that. I'll show you in a minute. If I have f of t, let's take the cosine as an example. Cosine 2 pi t. If I multiply this by delta of t, what does this do? What is the value of this for all values of t except for 0? What is it equal to? 0. This is the definition of the unit impulse function, isn't it? It's equal to 0 everywhere except for t equal to 0. So I know that the product of those two will be 0 everywhere. And if I have, again, if I sketch it, let me sketch it like this. A very thin curve. This is the unit impulse function. And the cosine, I'll sketch it here. Can you tell me what is the product of those two for all t except for 0? Leave 0 for the time being. What is it equal to?
0.
0. 0. Absolutely right. Yes. It's equal to 0 here and 0 there. Now, the only point where it's not equal to 0 is the point at which the unit impulse function exists. Or let's say it's not equal to 0. It goes to infinity. Now, at that point, I happen to have a unit impulse function that is multiplied by a cosine with a specific value at that point. Now, how much is the cosine at t equal to 0 exactly?
It's 1.
It's 1, absolutely.
1.
So if you multiply this cosine, yes, you're right. If you multiply the 1 in here by this unit impulse function, what do you expect will happen here? تفضل عبد الرحمن.
It will be just the unit impulse function.
Absolutely right. So I'll end up with the unit impulse function as it is. طبعا, clearly, the unit impulse function here has been multiplied by the value of the function at that point. It just happened that the value of the function at that point was equal to 1. Assume that this was not a cosine. assume that it was equal to x. Let's say, let me see. I want a function that is
Sine.
no, sine happens to be 0 at that point. I want something that is in between. For example, or something that has, okay, 3x. Let's say 3x. Assume that I multiplied it by 3x. No, 3x. No, even 3x is not going to work. 3x minus 1. Let's say 3x minus 1. Or 3. Yeah, 3 x minus 3x plus 2. Let's say 3x plus 2. Right? So I multiplied the unit impulse by 3x plus 2. Now 3x plus 2 at x equal to 0, 3t. I'm sorry, this should be t. 3t. 3t plus 2. Okay. Sorry, I'm using different colors. My apologies. Okay. At t equal to 0, the value in here will be equal to 2. At t equal, and this is basically how it will look like. But if I multiply the 2 by each other, we said that it would be equal to 0 in here and 0 in there. The only place where it's not equal to 0 happens to be at 0, because the unit impulse function is not equal to 0, and this is also not equal to 0. Now this happens at t equal to 0, happens to have a value that is equal to 2. This is a function now. And it has a value that is equal to 2 at t equal to 0. So I'm multiplying the unit impulse function by a value that is equal to 2 at that point. So what do you expect I'll get in here? I'll get 2 delta of t. Exactly, this is equal to delta of t. This has values that change for different values of t. But all I care about is the value of that function at t equal to 2 exactly. All other values are not important. And I'll end up with a function at the end that is equal to the unit impulse function multiplied by the value of that function, of that thing, evaluated at t equal to 0. Yeah, as if this unit impulse function say, yeah, function nt, which comes before me, I want you only, or I'm only interested in one of the values, one of your values. What value I'm interested in? I'm only interested in the value in which I am not equal to 0, which happens for this delta of t. This delta of t is not equal to 0 only at t equal to 0. So basically, as if it lends its location to this. So it basically comes and sets the t there to become equal to 0. And you'll end up basically with the following. Where did I write it in here? Any function f of t, when you multiply it by the unit impulse function, delta of t, you'll end up with f of 0 multiplied by delta of, I'm sorry, this is delta of t. Multiplied by delta of t. Whatever f of 0 is. Now this is for if the delta happens at t equal to 0. What if I have f of t multiplied by delta of t minus t0? Can anyone guess what this is going to be equal to? Muhammad al-Jari.
F of t times delta t.
F of t.
Yes, f of t naught.
Yes. You're absolutely right. F of t0 multiplied by the remaining delta of t minus t0. What is this basically saying? It says to this, I don't care about all of your values. All I'm interested in is only the value in which I exist. And I exist at t equal to t0, because this is a shifted unit impulse that happens at t0. So I want you only to multiply me by your value at that location. And this is basically why this becomes f of t0. Okay? Multiplied by, this does not change. This is exactly the same. It still remains. The delta is still there, or the unit impulse function is still there. By the way, the unit impulse function is always given the symbol delta. This is delta. This is a Greek letter delta. Okay? So the unit impulse function says to the f of t, I'm only interested in one of your values, which happens to be at t0, because this is where I exist. All of your other values can be just ignored. I don't care about them because I'm going to multiply them by 0. So they'll disappear. And this is why f of t changes to f of t0. Now, does it mean that if you write this as it is, if you leave it as it is, it's wrong? No. Think of this as a simplification to this. The right-hand side, the one that I'm going to color here in red, This is a simplification of the blue part. Why is this a simplification? If I ask you to integrate this, for example, from minus infinity to infinity. Oh, what did I do? Okay. If I ask you to integrate f of t delta, okay, I'll come to, I think one of you has raised your hand or what? Okay. F of t delta of t minus t0, okay, dt. If I ask you to integrate this, you see this is the product of two signals, two functions. I know what the delta is and I know what f of t is. But if you know the integration of cosine and you know the integration of tan, it's the integration of cosine times tan is not equal to the integration of cosine multiplied by the integration of tan. The integration doesn't work this way. You'll have to find what is the product of the two is, and you'll have to use some of the calculus, let's say, techniques that you have studied in math 101 and 102 and so on to find this integration. But if you use this simplification, you can do this integration very easily. We said that this thing becomes equal to the integration. I'll just replace it with what it's equal to. It's equal to f of t0 multiplied by delta of t minus t0, right? dt. I just said that, okay, this delta gave its location to the f of t and made the f of t equal to, and it doesn't care about f of t, it only cares about the value of f of t at t0. Now, can you tell me what is this? Is this a function of time? Clearly not. It's not a function of time, isn't it? This is a constant. It's 3 or 5 or 0 or 10 or whatever value it is. When you evaluate any function at t equal to 5 seconds, you don't get a function of time. It becomes a constant. And because it's a constant, I can take it outside. So what remains for me is, so I can do this. So this becomes equal to f of t0 multiplied by the integration of what remains inside. And what is this integration equal to? تفضل يا محمد البوري. Exactly. This was one of the things that we defined the unit impulse function with. Any unit impulse function, طبعا I'm assuming here you're integrating it from minus infinity to infinity. Yeah? If you integrate a unit impulse function from minus infinity to infinity, you'll always get one. What if, okay, basically this becomes equal to f of t0. You see, I was able to use this simplification to find what this is equal to. Without the simplification, you wouldn't be able to find it. Okay, fine? So basically, this becomes equal to, I could write this as f of t0. Yeah? In fact, this is one of the properties also of the unit impulse function. Okay, you see, we have talked about this. Right? We talked about this. Yeah. By the way, this is called the sifting property. I didn't write the name because I'm sure that most of you will probably not understand what it means. Okay, but if you go to the English and search for sifting, you'll understand what it does. Yeah. What is the meaning of sifting? Anyway, this is called not shifting, by the way, sifting with an S. Sifting. Okay. This is called the sifting property. This is called the sampling property. If you have any, I don't know why I'm using capital T here. Yeah, this should have been T0, right? And this should have been T0. I copied it from somewhere else and I forgot to change this. T0, T0, and this T0. Okay, which is exactly what I told you about. This property is, think of it as sampling. If you want to know what the value of a specific function f of t at t equal to 3, for example, all you have to do is multiply it by an impulse function that happens at t equal to 3 and integrate the result. You'll end up with the value of that function at the output of that integrator. Okay? This is basically what the meaning of sampling. Okay? Now, the unit impulse function is related to the unit step function. In fact, we can get the unit step function from the unit impulse function, and we can get the unit impulse function from the unit step function. And I'll explain them to you this way. Let me go to the unfortunately, okay. Let me go in here. If someone asks you Find the derivative of, can you tell me what is du of t, or dt by dt of u of t? What is the derivative of the unit step function? What is the derivative of the unit step function in here? The blue line. What is it? Yeah.
0.
0. Why? It's a straight line. A line, let's say, that has zero slope. I mean, so not straight line. Straight line is not the appropriate term. It's a line that has a slope of 0. Because a straight line may not have a derivative that is equal to 0. I mean, this is a straight line, but it doesn't have a derivative that is equal to 0. The derivative is the slope, right? This does not have a slope that is equal to 0. It has a slope of 1, 2, whatever, okay? But it's a line that is horizontal. It has 0 slope. So clearly, the derivative of the unit step function is equal to 0 in here. For all t that is negative. What about for t that is greater than 0? Abdurrahman?
The change for the unit step function at t equals 0 is 1. So it's equal to 1.
لا لحظة. And I'm asking you here for t now greater than 0. For t
greater than 0.
Positive. Yeah. How much is the derivative?
It's 0.
It's 0. Absolutely. Okay. So the derivative, you see, the unit step function is the unit step function has a derivative that is equal to 0 for t less than 0, as well as for t greater than 0. Does it mean that the unit step function is always, its derivative is always equal to 0? No. Then what's the difference between the derivative of the unit step function and another function that looks like this, for example? This. This has a derivative that is always equal to 0. But the unit step function has a derivative that is always equal to 0 except for t equal to 0. And this is what Abdurrahman mentioned. At t equal to 0, you jump vertically from 0 to 1. What's the derivative of a line that is vertical? What is the slope of that line? Abdullah?
It's undefined.
Well, okay, undefined. This is one way of thinking about it, or infinity. صح? It has a slope that is equal to infinity. صح? Okay, because think of it this way. This line has a slope that is equal to 0. This line has a slope that is equal to 0.5. 45 degrees is a line that has a slope of 1, slope of 2, slope of 3, slope of 5. Okay, as the line becomes more vertical, the slope increases until you have a vertical line which has a slope of theoretically infinity. So you see, the derivative of the unit impulse function, think of it this way, it gives exactly the unit step function. When you differentiate it, you get the unit impulse function. That's why the next property says this. How do you get the unit step function from the unit impulse? Okay. Sorry, I did the opposite. Okay, how do you get the unit impulse from the unit step? Okay, you differentiate the unit step, you'll get the unit impulse. Now, if the unit impulse is obtained from the unit step by differentiating, then how do I get the unit step from the unit impulse?
Integration.
By integration, exactly. And this is how you write the integration. U of t minus t0 is always equal to the integration, not from minus infinity to infinity. And this is what you would probably think of delta of t minus t0 dt. Most of you will probably think this, but that's not true. If you integrate the unit impulse function from minus infinity to infinity, what did we say you'll get?
1.
You'll get 1. But the unit step function is not always equal to 1. This is why I have to change this upper limit to t. And since I have t there, usually they change this to tau or some dummy variable, or alpha, for example. This is just a dummy variable of integration. It does not appear in the final answer. So clearly, if t is less than t0, think of it this way. This, if I sketch it, the delta function, okay, it happens here. If t is somewhere in the left, what is the output of integration? You're integrating from minus infinity to a value that is, this is t0, that is less than t0. How much are you getting when you integrate the unit impulse from minus infinity to a value that is in which the unit impulse has not occurred yet. How much do you get, Muhammad?
0.
0, absolutely. Yeah. So the integration of the unit impulse, gentlemen, is 0 as long as the unit impulse is not inside the integration. Only when t becomes greater than t0, then you are integrating from minus infinity all the way to somewhere in here. In this situation, you are including the unit impulse in your integration, which means that the outcome becomes equal to 1. And that's why you end up with all values in here from minus infinity to t0, you get 0. And this is the result of the integration. All values from minus infinity to t0, I get 0. For values from t0 to infinity, I end up with 1, which is exactly the unit step function. Okay? So those are basically the two properties of two more properties of the unit. Let's say two properties that relate the unit impulse with the unit step and the unit step with the unit impulse. The last property basically says that the unit impulse is a symmetric function around its location. Yeah, meaning that if I have a unit impulse that happens at t equal to 0, yeah, if I flip it around itself, it is exactly the same. Like the cosine, for example. The sine is not symmetric. It's not an even function, the sine. The cosine is an even function. This basically says it's an even function. Okay? Even if you have a signal that is located, for example, at t equal to 2 seconds, a unit impulse that exists at 2 seconds, and you flip it around, it's around 2, not around the 0. Clearly, if you flip it around the 0, it will come here. But around the 2 itself, if you flip it, it will remain the same. Okay? This is basically what the last property says. So those are the properties of the unit impulse function, and we have talked about the other functions. Okay? Now, I'll talk about the last one, the last function, which is called ramp. The unit ramp. Where is it? The unit impulse function. Okay, the unit ramp function. Now, the unit ramp function is not that difficult to understand. It's defined usually as an R of t, and this is how it's defined. It's similar to the unit step function. If you remember, the unit step function was like this. This t0. The following, let me sketch it in two different color. This is u of t minus t0. The unit ramp function, I'll sketch maybe in blue or so. Yeah, no, in green. Yeah, the unit ramp function, gentlemen, looks like this. It's again 0 in here. Yeah, but at t equal to t0, yeah, this is I'll call it r of t minus t0. Yeah, it increases linearly like that, like a straight line. Yeah, so it has a slope of 1. In fact, the slope here, slope equal to 1. Now you can, your book, by the way, writes it in a different way. Yeah, your book, instead of writing it as r of t minus t0, it writes it as a different, slightly different way. It writes it as t minus t0 multiplied by u of t minus t0. If you think about it, you see the green line in there. Yeah, you can obtain it by multiplying this line that goes from minus infinity to infinity, and this line is nothing but t minus t0. If you multiply it by the unit step will cancel all of the negative part, and it will only leave the positive part. The negative part becomes equal to 0, and the positive part increases linearly, so you end up with exactly this r of t minus t0. Or basically, I can write it this way. Okay, Juan? So this is the unit ramp. Now, unit ramp, I'll write this inshallah later, okay? It's related to the unit step function. You notice that the unit impulse was related to the unit step function, either by derivative or integration. What do you think the relationship between the unit ramp, this one, and u of t minus t0? Anyone can spot that relationship? What will I have to do? Let me maybe give you a hint. If I have the ramp, what should I do to it to get the unit step? Fadal Abdurrahman.
Divide by the argument of the ramp function, which is
okay. Yeah. I want maybe give you a hint. Integration derivative. Can you use integration derivative to come up with that? What you said is yes, right, but this is not the way of relating them that I want.
Oh yes, yes. The derivative of, in this case, it's a straight line. Y is equal to x.
Yeah.
The derivative will be
Okay.
it will be 1, but
Yeah, you're right. The derivative, you see in here, the derivative of this is 0, صح? Which is exactly the step. And here, the derivative of this is a straight line. Its derivative means the slope. What is the slope of that? I just told you. It's equal to 1. So what's its derivative? It's exactly 1 for all values of t greater than 0. صح? Which is exactly
Right.
the step. So in fact, if you differentiate the ramp, you get the unit step. Which means if you integrate the unit step, you get the ramp. Which means the following, and maybe the last thing that I want to mention in here, and I have about 10 minutes that I'll try to solve a problem for you, okay? If I have, let's say, delta of t, not d of t. Oh, okay, delta of t minus t0, u of t minus t0, and r of t minus t0, okay? If I integrate in here, integrate the unit impulse, I get the unit step. Integrate again, you get the ramp. Yeah? If you differentiate the ramp, yeah, you get the unit step. If you differentiate the unit step, okay, you get the unit impulse. Now you cannot differentiate the unit impulse. The unit impulse function is non-differentiable. You cannot differentiate it. It already goes to infinity, and you cannot differentiate it. And let me leave it at this. Okay. So this is basically how the three are related to each other. And we have already seen that the probably I'll add this graph later, or this figure. It just came to my mind. I can obtain the direct function from the unit step function, by adding 2 unit step functions. In fact, you can even multiply 2 unit step functions to come for direct. Okay, so this is how the 4 functions that we have talked about are related to each other. Okay, right. Now what I will do is I will not go to the next topic. The next topic talks about systems, and I'll talk about it inshallah next class. Let me just talk about. Let me give you an example. And kind of, I used to give this example. This topic, by the way, was taught in EE201 or 202, the circuit course, when I was a student. When I was a student, this topic used to be in that course. Then the course changed, I'll say at least 5-6 times from the time I was a student when I took the course in here in KPPM, and many years before you were born. Okay, in 1991, I think. 1991, not 2001, 1991, right? Because I entered KPPM in 1989, and I think I took it the second year or something like that. Okay. Anyway, this topic, this example was in fact part of circuits, electric circuits, and then the course changed and they removed it from it. This is basically what the example says. Unfortunately, I don't have it written. Yeah? Example. Use red. I think I mentioned to you that I like to use red, and the reason why, it wakes you up. When you see red, I'm hoping that it keeps you awake. Like example, okay, given the signal below, the signal x of t, let's say, below, write it in terms of sum of unit impulse, unit step, and unit ramp function. Okay, so I want you to use 2, 3, 5, 10 unit step functions, unit impulse functions, and unit ramp functions as you wish to represent the following signal, x of t. Now, how does x of t look like? It looks like the following: minus 2, let me start with minus 3. 1, 2, 3, 1, 2, 3, 4. There are several examples like this, by the way, in the book. Minus 4, minus 3, 2, minus 1, 1, 2, 3, 4, and this is x of t. And x of t looks like this. Let me use a different color, maybe green. Thick green. Okay. I have 0 in here, and then suddenly in there, certainly I'm not going to be able to finish this, but let me at least give you the idea. And let me add in here something that looks like this, and something in here that looks like this. Okay, I think that's enough. Where this is equal to 1, this is equal to 2 in here, this basically, okay. And this is minus 2, and this is also 2 in here. Okay, and I think I have labeled everything. Okay, I only need to tell you that the unit impulse functions have magnitudes that are equal to 3 and minus 4, something like this. Okay, now I want to represent this. By the way, this is relatively speaking complicated. Yani if I give you a problem like this or so in an exam, it will be probably simpler than that. Right? I want you to represent this using unit impulse functions, unit ramp functions, and unit step functions. If you notice, everything that exists there are straight lines. I don't have curves. If I had curves, I wouldn't be able to represent it using those three. Because those three, if you notice, they are straight lines. But there are a lot of signals that happen in the lab that are exactly like this. Now, can anyone tell me how can I start? At least give me a hint. What is the first function that I need to add so that I can track? Think of it this way. Maybe I'll just give you a hint. What you need to do when you're solving a problem like this is always start from minus infinity. Go to minus infinity and increase time. Go to minus infinity, gentlemen, and keep increasing time. And see, as you're increasing time, whenever you see a change in the signal, think, what should I do? What should I add or subtract so that I affect that signal? And what should I add or subtract to whatever components I already have so that the signal changes from whatever behavior it was going to do to the new behavior that I'm interested in getting. Yeah, I'll just maybe give you a hint. Maybe I'll start with 1 or 2, and then probably whatever time I have at a specific point, I'll just let you try to do it yourself, okay? And I promise you that I'll put an example in the lecture notes that will explain this hopefully in detail. Okay? Now I'm starting from minus infinity and I'm increasing time. 0, 0, 0, 0, 0. So I do not need to add anything, because if you have a signal that is equal to 0 and you add nothing to it, it remains 0. Right? So I'm adding 0, 0, 0, 0, 0 until this point, until minus 4. At minus 4, I notice that suddenly I jump from 0 all the way to a height that is equal to 1. Notice that the height here is equal to 1 because of this. Right? Which of those three functions will allow me to jump? Will the unit impulse function allow me to jump? Jump and remain at that point, by the way. The unit impulse function will allow me to jump, but it will allow me to jump to infinity and will go back to 0. So I shouldn't add a unit impulse function there. What about the ramp function? Does the ramp function make me jump from wherever I am to a different location? What do you think?
Yes, but with the slope.
Yeah. First of all, it doesn't allow you to jump. It provides you with a slope. If you think about the ramp, how does the ramp look like? Is there discontinuity in here?
No.
No. The ramp function does not provide you with discontinuity. This is why if you see a jump, a vertical jump, this means by default you are talking about a unit step function. Either plus or minus, this is another issue, okay? But whenever you see a discontinuity, a jump upwards or downwards, this means a unit step function is added there or subtracted. Whenever you see a change of slope, this means a ramp is added or subtracted. So in here, clearly there's a unit step function that has to be added so that I jump from the 0 that I was at to the new location, which is the 1. So in here, clearly I have u of t, but it's not u of t, it's u of t shifted to the left by 4 units. So u of t plus 4. So this is the first thing that I have to add in here. Now, if I just leave this, what will happen? I'll go up and I'll continue like this forever until infinity, flat at 1. But I noticed that at minus 3, two things happen. First of all, I have this. And what is this? What is this function, gentlemen?
Impulse.
Unit impulse, exactly. With what magnitude?
-4.
3.
Minus 4. So no. This is the location of it. It has a magnitude of 4. The area under it is 4, but in the negative side. So I have to subtract it. Minus 4 delta of t, but it's not delta of t. It's delta of t shifted to the left by 3 units. So delta of t plus 3. But something else also happens here. You see, if I only had the delta, I will continue at 1 forever. But something happened. At t equal to minus 3, suddenly also the slope changed. صح?
صح.
The slope changed from a slope of 0 to a slope. How much is the slope in here? How much is the slope there? How can I find the slope? تفضل عبد الرحمن.
It is y2 minus y1 over x2 over x1.
Absolutely.
In this
You can probably find it easier. Look, in 1 unit in here, I went up by 1 unit. So what should the slope be?
1.
1. A positive 1. Okay. So I have to add a step function here or what?
Ramp function.
Ramp function, exactly. I have to add a ramp. Yes, exactly. R of t minus, I'm sorry, t plus 3. Now, if I just lift it at this, it will continue forever like that. But what happened at this last one? I will do at t equal to minus 2. What happened? Did I jump? No. There's no discontinuity, so I shouldn't add step functions. But the slope changed. What is the function that I should add here? Anybody can maybe give me a hint? تفضل حسين.
Ramp function.
Okay, tell me. You said ramp. So plus or minus?
Minus.
Minus. What is the magnitude here? How much should I put? 1 ramp, 2 ramps, 3 ramps?
3. Minus 3.
Why 3? Why minus 3? You're right, but why minus 3?
It is the slope is 1, and they want to change it to minus 2.
Absolutely right. You notice? You see, the slope that I was going with was equal to 1 already. If I just subtract 1 ramp, it will make it flat. If I reduce 1 more ramp, it will make it minus 1. I need to add, let's say, subtract a 3rd ramp to make it minus 2. If you notice in here, by the way, the slope here is minus 2. I'm going down 4 units in 2 seconds. So the slope is minus 2. So I need to subtract minus 3 ramp, and this ramp happens at t minus 2. And so on. And you can continue now by adding and subtracting until you complete all of this. Okay? So I'll stop here. I'm sorry, I took 2 minutes from your time. My apologies for that. Again, I'll give you a quiz. I'll tell you, inshallah, tomorrow about the quiz. The quiz will be, inshallah, tomorrow I'll tell you about the details, but the quiz is not going to be on Thursday. The quiz, again, will be on Sunday of next week. Okay, Juan? So it looks like I'll have to set up the syllabus, or I'll adjust the syllabus. So inshallah, I'll let you know through the WhatsApp or some other mean about the details about the quiz. Okay, Juan? Okay, yeah, have a good day. If you have any questions, I'll remain online. so please تفضل محمد.
تقدر يا دكتور تعدل الطريقة اللي نقدر نحدد فيها السلوب بسرعة يعني.
اوكي ولا يهمك ان شاء الله. اوكي طيب what is the slope? The slope طبعا when I asked, I think عبد الرحمن mentioned the slope is y2 minus y1 divided by x2 minus x1. Yes, this is the slope. It's delta y divided by delta x. But an easier way, especially with straight lines, to find the slope is this. Okay, look at 2 points in which the straight line passes. For example, this point and this point. This point, okay, and look between those 2 points. How much did you go up? This is the delta y. I went up between those 2 points, for example, 5 units. How do you know? Assume that this is minus 2 and this is plus 3. So minus 2, minus 1. Sorry, it's not to scale. 1, 2, and 3. So between those 2 points that I'm looking at the line, I went up 5 units. In how much time? Assume that this was minus 1. Let's say this is 0, this is 1, and this is 2. I went up by 5 units in how much time? In 3 seconds. So the slope becomes equal to 5 over 3. If you're going up as you go to the right, then the slope becomes positive. If you were going down, exactly the same process, but then you put a minus sign in front of the slope. Did I?
اي وضحت يعطيك العافية.
Okay. حياك الله. الله يحييك. Any other questions, gentlemen?
دكتور
تفضل محمد.
انا عندي مشكله لكنها خارج الدرس يعني خارج الليكتشر، فاذا خلصت الاسئله ابغاك لها.
تفضل ولا يهمك. Anyone else has any question on the course or so? Anybody has any questions, gentlemen?
معلش يا دكتور السلوب ماينس ولا بلس؟ ماينس 5 over 0.
Okay, اتذكر هذا السلوب I was talking about this line, a line that increases as you go to the right. As time increases, the line increases. يعني the value of the function increases. It has a positive slope. The opposite is true. If as t increases, the line drops, then the slope becomes negative.
تمام.
Okay. Any questions, gentlemen? Any other questions? Badr? Badr? I cannot hear you. I don't know. Maybe if your microphone is has a problem. I cannot hear you. If you want, you can. I don't know. If it's a short question, you can send it to me in a message. Anyway, it's okay. Don't worry about it.
Doctor, I sent a question on WhatsApp about the quiz.
About the quiz?
Yes.
Which quiz? Coming quiz or the last quiz?
No, last quiz.
Last quiz. What about it? وش فيه؟ لسه والله ما صلحته والله حتى I didn't even check it honestly. وحتى الكويز اللي حق الother course لسه ما صلحته لأنه والله yesterday I spent a lot of time working on your lecture notes. أنا lecture notes هذه تعهدت إني راح أعملها والآن ندمان بس خلاص يعني الآن it's too late to go back. لأن يعني الحقيقة أنا I'll tell you when I'm reading the book even to prepare the notes I keep thinking لو ما عملت النوتس هذه probably you'll get lost. And the reason why, it's not because the book is bad or... لأن الbook sometimes goes into details that I think are not that important. And على الأقل أنا بالنسبة لي it's good to know, but if you don't know them, it's not a big deal. فلهذا السبب what I'm trying to do as much as possible in the notes is only focus on the things that I'm interested in. يعني I'm planning to give you the notes بحيث أنكم تعرفوا الآن بالضبط what you're going to be asked. And what questions you solve or so you can go to the book and solve questions related to what you have in the notes. فanyway لهذا السبب والله it took from me so much time yesterday last night وحتى اليوم الصباح والله جلست قبل الكلاس from early in the morning I was working on the notes. Okay طيب لسه لحد الآن ما I didn't do anything in it. Do you have a question on it ولا can you wait شوية؟
No, wait.
Okay, I promise you, inshallah, in the next 2 days or so, inshallah, hopefully before the next quiz, you'll have the results for this quiz. My apologies for that. Okay. Badr, I saw that you sent a message, but let me see what you wrote. Okay. let's see. ماذا الدكتور؟ لا اوكي. لقيت نسخة إلكترونية للكتاب فمن ما أنا متأكد إذا هي المعتمدة في الجامعة هل ممكن أرسلها؟ ما في مشكلة. اوكي. هي أنا خليني أقول لك أنا I also found الحقيقة والله one of you asked me if I can send or يعني if I can give the if there's an electronic version of the book, and I told him that I downloaded a version. Okay, so I have it with me. بس أنا طبعا ما يعني ethically خلينا نقول أو from لحظة. I'll do something. I have to حتى ما يؤخذ عليه.